Hey everyone, we are excited to present PALM, Progress-Aware Policy Learning via Affordance Reasoning for Long Horizon Robotic Manipulation, our CVPR 2026 work. This is a joint work between UPenn, UIUC, NTU, University of Oxford, and MIT. Vision language action models, our VLAs, have made strong progress on short horizon tasks, but still break down on long multi-step manipulation. On something like clean a clutter table, state-of-art policies start well and fail midway. So there are these core gaps. VLAs lack reasoning about which object, where to place it, and how to move. So they can't track within subtask progress. And together, this produces repeated actions, skipped steps, and premature termination. The root cause is that vanilla VLA collapses many distinct task spaces into a single policy mapping observations to actions. With no internal notion of stage, visually similar state becomes ambiguous. So the model cannot tell whether to keep grasping, switch to placing, or stop. Cumulative errors then push the next subtask start state out of distribution and rollout falls apart. So we need a policy that knows what to attend to and how far along it is. And PALM is our answer. So it's an end-to-end VLA with two slightly coupled ideas. First, a structured future affordance module that predicts the um, the task-relevant interaction queues, which includes object relevance, contact geometry, spatial placement, and motion dynamics. Second, a continuous within subtask progress estimator that tells the policy where it is in the current stage. Together, they enable temporarily consistent multi-stage execution and deliver state-of-art results in simulation and the real-world settings. Here's the architecture. So PALM takes three synchronized inputs, a language instruction encoded by CLIP, an RBG observation coded by a masked autoencoder, and a downsampled with a perceiver resampler. And the robot stayed through a small MLP. So these tokens are fused by a GPT-2 style transformer backbone. On top, we introduced two learnable query sets. The first is the fine-grained foreign query with four subqueries: global, local, spatial, and dynamic. Global identifies the reference subject, supervised by grounding Dino and SAM tasks. Local predicts a contact likelihood heat map following Glover spatial outputs candidate placement points using spatial VLM and Robo point. Dynamic forecast which pixels and gripper and movement sub objects will move and supervised by the code tracker trajectories. The second is an action progress query. So it conditions on the affordances latent and feeds a denoising diffusion transformer that jointly decodes the end step action sequence and a continuous progress scalar between 0 and 1. In one forward pass, Palm forecasts where to act, what to do, and how far along it is. We evaluate on two long horizon benchmarks. First, Kelvin ABC to D, where models pre-train environments ABC and test on unseen D. So Palm reaches 96.9% success on the first subtask and 82% at the five task horizon. So it's a 17.7 percentage absolute improvements over the strongest prior baseline. Sear, the next benchmark, our average length is 4.48, beating Sears 3.998 and Pi Zero's 3.92. So removing the progress signals drops average length from 4.48 to 4.02, confirming progress prediction is doing real work. On Libro, across all suits, spatial, object, goal, and long, Palm hits 94.8 percentage average success rate, state of art, and the headline number is liberal loan at 91.8%, beating the strongest baseline COT VLA at 69% by 22.8 points. Across spatial reasoning, object grounding, and extended horizons, structured affordances plus progress supervision deliver consistent gains. Beyond simulation, we built a real world model platform, UFA CORY X-Arm 6 with a Gripper G2 and two RealSense D455 cameras. One eye on hand, one eye on base. We fine-tune on 200 in-house demonstrations and evaluate on a six-step pick and place task under three generalization stresses: random localization, visual destruction, and unseen lightning. Baselines are OpenVLA and Octo, both fine-tuned on the same data for fairness. Across all three settings, Palm is roughly 2 times better than the baseline. So under random localization, Palm's average length is 3.05 versus 0.995 for OpenVLA. Under visual distractions, 3.8 versus 1.6. Under unseen aligning, 3.55 versus 1.25. The baselines collapse to zero by the fourth or fifth subtask, while Palm still completes a sixth subtask 30 to 40 percent of time, exactly the kind of tail long horizon deployment requires. The three video shows, Palm rolling out on the same six-step sequence under the original condition. Then under unseen lining, visual destruction, and random localization, notice that Palm keeps tracking the right object, transitions between stages cleanly, and recovers when distractors enter the scene. So these are the behaviors that a baseline simply can't produce. To wrap up, Palm couples structured future affordance prediction with continuous progress estimation in a single closed-loop VLA. So the results is stable subtask transitions, a 12.5 percentage improvement on Kelvin APC to D, 91.8% on liberal long, and roughly 2 times gains in real-world long horizon generalization. So thanks, come find us at the poster.